Okay, so we are at the top of this hour. So hello everybody and welcome to our second DES presentation of this year. We're here for a special presentation today. But before we get started, I'm here to introduce to you the host. I'm sure you all know him. It's Dr. George Mason. He's been around in the thermomechanics community since 40 years, I guess, by this time. He was a part of the U.S. Army Corps of Engineers, ERDC, ERDC. He's been there for 30 plus years before he retired from there. He also joined CAVS after that, Mississippi State University, and he's been there for some time. But he's around doing some stuff. He's very active with ISTVS, and he's here to host this session for y'all today. So we'll continue. Dr. Mason.
Greetings from the United States of America. I know we have people from Europe and other places. It's early morning here, around 8 o'clock my time. I think it's late afternoon over in Europe. But we have a good speaker today. He's going to talk to us about sensors and how they're modeled in simulations. Phillip Price comes from the Mobility Systems branch. It's a part of the R&D Center with the Engineering Development Center. It's with U.S. Army Corps of Engineers. So the Army has a R&D section that works with sensors and mobility, and an entire mobility branch dedicated to looking at vehicles, off-road vehicles, on-road vehicles, and how they can be traversed. They got into autonomous ground vehicles a good bit, about 20 years ago, and have worked through sensors and implement them in simulations. So Phillip will talk to you. He's out of the University of Kentucky. He also went to school at Auburn University, where he has his degrees in physics and math. So I present to you Phillip. Before I do, I guess one last thing, we have a chat box here. Often I'll put questions in there, or I encourage that the people watching just put their questions in the chat box as Phillip talks. And at the end of the talk, we will bring them up and go through them one at a time or ask for questions. So without any further ado, Phillip, the stage is yours.
All right. Thank you, Dr. Mason. Just make sure I am still coming through audio, right?
Yes.
Okay.
Sound good.
All right. Thank you. So, yes, what I will be talking about, a brief talk today about sensor simulations in support of autonomous ground vehicle modeling and simulation tools. Just sort of a brief overview of kind of the approach at ERDC that we're currently using for creating these sensor models to inform the Army and other customers of how these autonomous vehicles will perform in whatever scenarios we're looking to make them perform. There we go. So yeah, just disclaimer, these views are my personal views and do not necessarily reflect those of the Department of Defense or its components. So, as sort of the first question we want to answer is sort of why are we doing modeling and simulation for these autonomous ground vehicles? Can't we just sort of do physically testing for them and get all the information we need to that way? Well, so they are of a major interest to the Department of Defense at the moment. Sort of, they offer protection, I guess, for the warfighter. If you can have a robot doing a dangerous job, that's one less person you put at risk. But these tasks are often highly complex in complicated environments, much more so than what you or I will typically encounter. And so we have sort of a need to test these vehicles, these platforms, and make sure that they can actually, they can do what they need to in these environments. And that is sort of an expensive and can be sort of a risky process to do physically. You sort of it's very easy and to do testing of an autonomous vehicle in sort of these wide open, nice, perfect field conditions. But unfortunately, that's not always going to be the case. Sometimes you're going to have to do a mission in at night, and it's when it's heavy rain, it's heavy fog, and we need to test and understand what this autonomous vehicle is actually capable of performing in these environments. So that is where sort of these modeling and simulation tools come into play. We can sort of create any sort of environment we want on the fly. We can add any vehicle we want, and we can go through any sort of testing procedure as many times as we want, which is often useful for these sort of autonomous vehicles, as most autonomy stacks are sort of stochastic in nature. And so we don't necessarily want to do testing just once. We want to do it multiple times to make sure we have a good window on sort of what exactly the vehicle is capable of. And so in order for these results to be useful, we want to make sure that these the results, the data that we're going to be giving for these autonomous ground vehicles is as accurate as we can. So, that brings up the question of how exactly do we do that? So this is sort of how I would sort of map out sort of our M&S tools. We have these sort of three components. We have the vehicles, we have the environment, and we have the sensors. So each three of those, we need to sort of have these sort of high fidelity models in. We need to make sure the vehicles are accurately modeled to make sure that they generate the right power. They have sort of the right weight, the right feel. We have the environment where we need to make sure that any environmental effects we want to model, outside light, rain, snow, all these things are modeled realistically. And then we have the sensors, how exactly, the sensors sort of perform the task of perceiving the environment and conveying that information to the vehicles. We need to make sure those are sort of all accurately modeled, and those link points are all accurate. The environment and the vehicles tend to interact with the environment through sort of this terra mechanics component. For us, that sort of comes in the form of these sort of speed maps to sort of tell us, okay, where can the vehicle go and how quickly can it move on them? The vehicle sort of will interact with the sensors through the autonomy stack. That sort of tells it, all right, what do I see and where do I think I can go? And then the sensors get that from the environment. They interact with the environment to sort of say, all right, what exactly do I see? And that is sort of the area that I'm going to be talking about. I'm sort of looking at the sensor development and how they interact with the environment, and how we can make sure that the sensor data that we're feeding to the vehicles and that we're getting from the environment is accurate. Yes. So there's sort of these various levels, I would say, of sensor fidelity. You have sort of at a lower end of sensor fidelity where maybe you're not actually perceiving them. You're sort of doing this this kind of abstract sort of viewing of them, where what you might do is you might say, okay, I can map out, say, the field of view of a camera or a LiDAR or a radar, and then I can assign statistical probabilities to objects and say, all right, there is, X% chance of perceiving this object in the field of view. That is sort of a low, this sort of lower fidelity model. I think this tends to be more used in sort of early testing, proof of concept stuff. If you're trying to, if you were sort of looking at developing a sensor, this might be a good place to start out. And then for our interest, we are looking more at the higher fidelity of sort of sensor interaction. We want to make sure that whatever data the sensor is getting is going to be the closest to what the physical unit is going to output, since that is what it's going to be, seen in the field. And again, reminder for us, we are looking at these very complex these vehicles that are designed to perform very, very complex processes, sort of very, very far away in very harsh conditions. So it's very important for us to make sure that we have as accurate a picture as possible, since any breakdown it costs a lot more for us to fix it than if a car breaks down on the side of the road or something. So that's what we are looking to do. We are looking to push and get these high fidelity sensor models. So how our approach for going about that is starting with sort of the fundamental physical theories for how these sensors operate. So sort of at the top, we have the sort of bidirectional reflectance distribution function. That's sort of for cameras. We're looking at how light scatters from all the surfaces, given what it's where it's coming from and what's viewing it. We have the radar equation there in the middle, which is sort of standard for how based the power that a radar output, what is it likely to get back, and what is it likely to see. And at the bottom, sort of a LiDAR equation, which is sort of the similar thing for a LiDAR beam outputting something, what power is likely to get back. So these are sort of the fundamental basics that are going to apply sort of, they sort of generically apply to any sort of sensor we're looking at. It's a good bet that all cameras that we're using, they're going to be reasonably modeled by this BRDF. All radars are going to be modeled with reasonably well with this radar equation, LiDAR similarly, but that's not enough. What we have found is that we typically need to collect experimental data. We have to take these sensors out in the field. We have to design experiments, and we have to process the data from those experiments to make sure that that we are able to capture any effects that are, I guess, sort of more difficult to capture, more difficult to model, and maybe sort of also hidden behind any sort of hardware specifics or company specific firmware. This is sort of where we go from what we call a spec sheet model, where we can look at sort of the generic data sheet that we'll get from a sensor, and then actually go to, all right, how is this sensor actually going to perform in the field? And that's sort of our higher order effect that for us is almost necessary to capture. Yeah, so is like one of the, yes, and this sort of approach is what we're applying to all of our sensors, the active and passive sensors. Cameras are typically defined as passive since they're not actively emitting anything. Active would be sort of LiDAR, radar, GPS, that sort of stuff. So we have sort of done this already with a couple sort of sensor model and environmental effects. So right now, one of the things we're currently working on, we are working to get dust visualization effects and how they affect the various sensors. And you can see sort of at the top left, we have sort of this theoretical understanding of how something like a LiDAR would see through a dust cloud, how the dust cloud would sort of affect its perception. You see these sort of four sort of scenarios where you have the LiDAR, they're seeing completely through the dust cloud, getting stopped by the dust cloud, sort of seeing both seeing sort of through it and also getting some of it, and then just get sort of getting lost in the dust cloud. And this is sort of one of the things we're looking to recreate and gather data on ourselves. So at the bottom left, we've conducted experiments where we've generated dust clouds with vehicles. We've set up our LiDAR to look at targets through it. And we have to figure out, all right, how does the physical data we've collected match up to these theoretical understandings that we have of this sensor and its modalities. So one of the things that's going to come with this that I sort of mentioned in the previous slide, one of the difficulties that comes with this, all of this data is sort of tied to the specific sensor that we used for this experiment. So while some of the fundamentals will stay the same, there is only so much we can do with this data. We can accurately say, okay, all of this second order effect will apply to the sensor model. But as soon as the ground vehicles pick a different sensor, then sort of this data will need to be collected again, because that's going to have different hardware, it's going to have different firmware, it's going to sort of similarly, these effects should be somewhat similar, but the higher order accuracy will sort of only be obtained by actually going out in the field and collecting this data. Similarly, we're looking at this for fog data. We're looking at how do sensors perceive objects in fog. So on the right there, you can see we went out to Point Reyes, California, and we looked at, we brought our sensors, we brought some targets, and we sort of looked at, okay, how do these sensors see the targets in this fog? It's a similar process though. We have our basic model, our basic understanding of how this works. And then we can gather this data to apply to a specific sensor model, but it comes with the caveat that this is tied to a specific sensor model. And so this is one of the things that we're looking to do with sort of many of the, as many of the sensor effects as we can. So all of any sort of sensor type and any sort of environment type. So we sort of LiDAR, LiDARs, radars, GPS. These are all common sensors. Then we have sort of these environment types, dust generated from vehicles, fog, rain, and snowfall is something that we're also beginning to collect data on. So yeah, and so that sort of brings up the question of how do we make a sensor model good enough? So sort of starting with this physics first baseline, that's to us that is a good approach. It allows it allows rapid development of more sensor types as the technology grows and changes. LiDAR technology may evolve, but a lot of the underlying physics will they will stay the same. There's no need to redo how light propagates through space. That's going to be the same for one LiDAR as it is for another. The tricky thing is, we do have to model and account for sort of this sensor hardware and sensor firmware that will sort of take the data from the physics informed data and do processing to it, and then that processed data is ultimately what is sort of captured and reported by the sensor. And so from our point of view, that is our goal. That is our metric of accuracy, because that's the data these autonomous vehicles are actually going to be. That's what these vehicles are actually going to be acting on. They're going to be acting on this sort of process, this sort of filtered filtered data in order to make their decisions and complete whatever mission they've been assigned. So one of the research problems I would say this brings up is, what is a how do we make a sustainable process for getting all of these sensor modalities to this high fidelity level that we expect and we're comfortable with when we're simulating vehicles for these complex missions. Is what I've showed you. Our approach relies very much on thorough testing of each individual sensor in order to reach that sort of a high fidelity state. But that is sort of somewhat inherently limiting, because that sort of takes time, that takes money, that is testing that we have to do in the physical world, which for the reasons I mentioned earlier is it can be expensive, not necessarily as dangerous, but it does take a lot of work. And so how do we how do we maintain this set of high fidelity sensors? That is sort of one of the questions that we're sort of asking. We tend to approach it. We will sort of have typical standards of sort of regression testing, but even still, with the rate at which software is changing on these sensors, not to mention hardware, this makes it very, very difficult to keep up. I know one of the things that we have been looking at, I think this was a paper that another one of our colleagues at ERDC has proposed for one of the ISTVS the ISTVS meeting coming up, is sort of looking at, can we, for a LiDAR, can we lay out these baseline effects that we have noticed in our testing to say, okay, this is our level of what does a high fidelity LiDAR model look like, and that is a reasonable first step. We can at least say, okay, we understand the effects this sensor models that are, you know, these happen in the real world. The real world, they are observable. But you know, there is still stuff we can do. There's still room to try and understand. Is there something we can do to make this easier and more generic, I guess. Yep. So yep, that's sort of all that I had. So it's sort of a quick tour of kind of the, you know, our approach for modeling high fidelity sensors so that they can go in these autonomous ground vehicle M&S tools, and the data, the results that we can get are somewhat reasonable and useful to the people that need them. Thank you.
Thank you, Philip. I guess, are there any questions out there? I'm looking through the chat box. I don't see any. I'll pose one while we're talking. Your sensors cover all frequencies, thermal up to visible, ultraviolet. Do they vary, particularly when you're trying to address fog and other conditions like that?
Yes. So we are looking to make sure that any sensor that is on a vehicle is accurately modeled, because it's likely that the autonomy stack that's driving the vehicle is going to be using data from that sensor to make its decision. So we need to make sure that yes, that data is there and accurately addressed. And so yes, one of the things we will look at is sort of, you know, it is the environmental effect on whatever wavelength that the sensor uses. You know, for the radars, it might be sort of the microwave gigahertz. LiDARs is typically just above, not quite infrared, but sort of that near infrared. And then yes, also thermal for all of the infrared stuff. And those are separate data points we do need to collect. It's somewhat, you know, it is, we can sort of collect those simultaneously. There's typically not a lot of interference between, say, you know, the LiDAR frequency and a radar frequency or a GPS frequency. So we can sort of, when we're doing these experiments, we can take advantage of multiple sensor modalities at the same time.
Along that same line of questioning, I see where Alex comes up. Alex King, Dr. King is asking, generally, how does LiDAR work in bad weather and poor atmospheric conditions, for example, storms and wildfire? You mentioned radar. I would think that if you look at the different frequencies, one may be better at cutting through poor atmospheric conditions than others.
Well, that's absolutely correct. And the way I would sort of, you know, the easy way to frame it, something like LiDAR, that's, for all intents and purposes, you can sort of treat that mostly as visible. So if it's difficult for you to see through it, it's going to be difficult for the LiDAR to see through it. The radar is you know, obviously different wavelength, different band, and so yes, so the radar will have it will have an easier time seeing through these sort of obscurant, sort of like fog, rain, snow. The trade-off that comes with that, though, any radar data you get is going to be much coarser. Let me Yeah, so in the bottom left here, you can see this is sort of LiDAR data, and you can see it's very, you get this very fine level of detail coming out of the LiDAR. Whereas with radar, typically what you would get, you would only get sort of single points. Like we have this truck in the upper left corner. You would get a single point from the radar that would say, this is what I get 1 point that we would associate with the truck. I see it moving at this speed, sort of at this position. And so that's sort of the trade-off space that comes with these different sensors, these different sensor modalities. They have their strengths, they have their weaknesses. Typically for us, in the defense, the Department of Defense space, one of the things that sort of comes into play is what's known as sort of active versus passive. So something like a LiDAR and a radar are active sensors, and basically what that means is they send out their own energy, which it's electromagnetic waves. The same, a potential adversary can detect that and then pinpoint where that signal is generating from. Something like cameras, on the other hand, do use, they typically use, they do not generate their own signal. They use ambient light from the environment, which makes them ideal because there's no way of detecting if a camera is in use. There are some, one of the things that is from the radar space that I mostly work in, there's this idea of a passive radar, where the idea is you make use of signals of opportunities and you avoid this active sending out of a signal. But obviously, radar we're blessed with the sun that generates all of this light in the visible spectrum, not so much in the microwave spectrum. So that can be a little less reliable as a source of signal for something like a radar.
Okay, Raju has a question. He may have to come on and explain it, but I think it says, I think it has to do with distinguishing between unmodeled physics and unknown model parameters. So I'm assuming this is a parameterization model we're talking about at this point, where I guess the question has to do with unknown information coming back, maybe noise filtering. Raju's trying to clarify the question. I think I got him typing a little bit. You're welcome. Are your models real-time capable? Oh, no, that's not really. Yes, he can speak. Let's see if I can figure out how to turn him on. Invite precipitant. Here's Varsha up there. Maybe Varsha can help us get Raju on.
Okay.
Well, there he is. There he is.
You can hear me?
Yes, sir. We can hear you.
So my question is this: on your last slide, you have this bullet where you say that you're using experimental data to enrich the models that you have with second-order effects, right? These are effectively unmodeled physics, things that you didn't capture in your original model, and you see a departure of the prediction of the model from the experiment, and you say, oh, we're gonna match them by adding some term that accounts for that. The problem, though, is that none of your models are first principle models, so they all depend on parameters. Now, you can get some of those parameters from the data sheets of the sensor, but some of them are not there. So you need to use experimental data to calibrate, to identify these unknown parameters that go into your model. And now the question is, well, so you have a model with some parameters, you have some experimental data, and you see that the prediction of your model does not match the experimental data. How do you know to assign that difference to unmodeled physics as opposed to not well-known parameters that you already have in your model.
Okay. Yes. All right. That is a very interesting question. It's a good. Yeah. So, because I guess it is. It is difficult. And I think one of the things that we tend to do, we tend to value, yeah, okay, I don't know if I should say that. I guess it really comes down to sort of trying to understand these the physics and the sensor models as best we can, and sort of looking at, okay, what is what research is there available? What do the companies kind of disclose about any of the technology, the hardware, and then we can sort of categorize it and say, okay, these are the effects that we, these are all the effects we understand need to be included. And then, once we can do that, once we can get that sort of this sort of spec sheet model up and running, that sort of is the known space, I guess. And I guess there's always, I don't know, I think that is something that I think we sort of could look into a little bit more. Trying to understand where where we're sort of discovering new physical effects versus improve or additions, I guess, to physical effects that we're already trying to model. Yeah.
In the old days, we would go to and you mentioned experimental data calibration process, but if it's real time, sometimes there's things like common filters and recursive filters where you modify the parameterization on the fly to adapt to unknowns. Have y'all looked at that? Is that in?
I'm sorry. Did you repeat that?
Common filters, recursive filters. Do you update any of the parameterization on the fly for your models?
I know we do have I'm not sure we've looked into that. I'm not sure that's a noticeable effect we've identified at the moment. I think part of this is sort of also, I guess, trying to keep up with the new technology as it's being developed and worked on. The state of LiDAR technology is constantly, it's constantly advancing. They're constantly developing newer and better sensors, newer, LiDARs, radars, all of this stuff. And so one of our concerns is making sure that, okay, we want to keep up with the current set of sensors that are actively being used. And so that sort of takes some of our time and focus as well. But that is a good point to try and look for, because I know we have seen. I mentioned looking at snowfall effects recently, And that is something I think we may have collected in some of that data, where the data we're getting from the LiDAR through snowfall is sort of, we can definitely understand. It's difficult to understand it through just sort of a physics, a physics first approach. And so that is sort of can be kind of where this internal filtering is happening. So yes, that would be a good place to try and look at this and see, all right, can we extract something from this data to tell us sort of how these internal parameters may be changing based on the environment that the sensor is currently in.
Just to support Phillip with this, because I'm also going to be a part of their branch. What I've seen, one of the things that the branch can do is really go out there and get a lot of data. So I think that is, I guess, the bridge that's going to help us distinguish between, say, the uncertainties that might be there in the physics that Phillip is presenting today, versus is it some of the parameters? It might be as you said, Dr. Radu, it might be the physics or the parameters. This is something we see even in simulation, and I do think that for them, it's the number of test cases that they have. I've seen their work. It's very thorough with the number of test cases, the amount of data that they have just for verification and validation that would really help them. And I think that sensitivity analysis and other stuff would help them on the way. But yeah, just to, support what Phillip is saying.
Varsha, can I make a comment?
Yes, yes, I saw you raise your hand.
That's all right.
Doctor. Yep.
Yeah, I'm outside, so it's probably going to be some background noise. No, great talk, and I wanted to make sure I get to hear you talk, Phillip. So that was good, and so that worked out. Now I was just going to mention that. So in my company, we do a lot with, let's say, NVIDIA simulation, modeling and simulation tools. You may have heard of the Omniverse, and for mobile robotics, for instance. And Omniverse, the Omniverse has a lot of out-of-the-box sensor models. It has a lot of out-of-the-box sensor models, and it's fairly easy and straightforward to connect those to a model of a mobile robot or ground vehicle, for that matter. And so I'm quite familiar with what you said, also about data as part of the modeling, using data as part of the modeling, because we can either work with data-based models for sensors, or physics-based models, or mixture of the two. So what we say in robotics a lot is we talk about gray box models, so which are both based on data and on rigorous equations, let's say closed form equations to describe the sensor model. So, but it's great. So, but just wanted to make that remark, yeah, that there are also like commercial packages in software to describe sensors and NVIDIA that are working on this Omniverse, that have developed this Omniverse simulation ecosystem. They keep expanding it and adding extensions and sensor models of this and that, including LiDAR.
Yep. Thank you. Yeah, I'm the Omniverse is sort of becoming a name much more well known over here. So yeah, good to know. Good to know. It looks like.
Did we answer all the questions? Did we answer Dr. Keen's question?
But so I think there's another one up there. Nico. Sorry, I couldn't. I don't know. I'm not going to be able to pronounce the last name. I'm sorry. Are the models real-time capable? Yes, that is actually one of the for us, actually, that is one of the constraints that we have when we're developing these models. And it's one of the things that sort of, it sort of, I guess, restricts us in a way in sort of how accurately we can model the physics of the sensor. You know, as a born and trained physicist, my initial reaction would be, well, you know, we can solve the Maxwell's equations in a discretized space to get sort of the most accurate, sort of the most accurate propagation of all of these electromagnetic waves. But in a real-time environment, that just, that doesn't work. You can't get it. We can't get that level of detail, and we need this real-time environment, because when we're working with these autonomy stacks, that's sort of one of the key things that we look at. We need to make sure that the autonomy stack, which in the field is going to be operating in real time, and so we need to make sure that the date we are giving it data as as accurate as we can, highest fidelity data in real time, to make sure that the autonomy stack decisions will reflect as accurately as possible what the vehicle is actually going to do. So yes, real time is a cornerstone for the models that we make in our sensors. And then I guess the last one from Dr. King, how much can pre-scanning terrain with LiDAR compensate for poor atmospheric conditions using pre-planned terrain mapping? I guess I'm not sure. So for pre-scanning the terrain, I do know one of the things we do when we're looking at the, when we're looking at the when we're looking at the sort of the environment piece of our M&S tools, when we create it, we do try and go out when we can to say, okay, if we're modeling an area, can we get the can we get the basically how a LiDAR sees it? A picture is sort of a camera gets a snapshot of how the RGB spectrum interacts with the environment that we have. We also try and get data for the LiDAR bandwidths, or the LiDAR wavelengths, sorry, and how those look at the terrain, and that is valuable for sort of the physical interactions. But a lot of but I mean, typically we do that in sort of these clear. We tend to do these in whenever we can get down there, and so it's unlikely that we're going to be able to get this data with any of these any of these sort of environmental effects we care about. So it's that that does serve as a baseline for the environment, and then we tend to use what's the word I'm looking for? We tend to use calibrated targets when we are conducting these experiments, so that we can relate the data we're getting to the various materials that we would see and that we have already mapped in the environment. Does that sort of answer your question there?
Alex, is that We'll take it.
I invited him to stage, so let's see.
All right. Good luck, Barsha. Yes, you can see. We just to mention when we close this out, Lutz is going to give us a short talk on upcoming events. Lutz is the president of ISTVS, and he's got his finger on the pulse of current ongoings.
Thanks for that introduction, George. Well, I'm supposed to know what's coming up. Right, Varsha, you're going to be sharing the material of the slides, because it's taken from an overview of society activities that was presented a week ago or so when we had a symposium at Iowa State University. That's why the title of the slide is talking about that. Let's go to the next page.
I guess I'll say thank you, Philip, for the talk.
Yes.
Thank you for the talk.
I was especially looking forward to it. Yeah, as I mentioned a couple of minutes ago. Thanks, Philip. Also about for the flexibility.
Sure.
With the dates.
For the flexibility. Thanks for having me.
ISTVS, what is it? I guess we don't spend time on this one now because everybody here in the audience is aware of what we do. So it was founded in the early 60s, non-professional society, terra mechanics and terrain vehicle systems. And we run a conference typically once a year. We work with Elsevier to publish a journal, peer-reviewed journal, Journal of Terra Mechanics. And we've got working groups, and yeah. Let's go to the next one. Right, and yeah, there's a long history, and when we had the 50th anniversary of ISTVS, we published something like a yearbook anniversary booklet. And what you see here is taken from that. I like the historical overview of what the community has been doing. These are pictures taken from the 60s and 70s and 80s, I guess, on the right-hand side. I think it's still possible. Yeah, it is actually possible to download the PDF version of that anniversary book through the website. I guess it's listed under publications. Next one. Right, so membership stats. We have currently around 150 members, individual members, fairly evenly spread across 3 regions. So we operate with regions. So the Americas, and then Europe, Africa meaning particular South Africa, and where we have a lot of activity, and Asia Pacific. And we're doing fairly okay. Obviously, we're trying to increase membership. Yeah, Varsha, let's go on to the next one. And we do have corporate members. So entities like corporations, but also research institutes that decided to become members rather than individual members. We also have corporate members. And with these organizations, with corporate members, we try to have close ties, understanding their needs, and they help us advertise the idea of ISTVS and the other way around. For instance, Algorithms, they joined last year, and it's kind of a success story because at this year's October ISTVS meeting, Algorithms are going to be running a pre-conference course on their product, which is a simulation tool for multi-body simulations of ground vehicles, including terra mechanics. I don't think they include sensors, as we heard about today, but yes, it's an interesting piece of software, and there's this course that they're giving just before the actual conference. Let's go on. Yeah, leadership, right. So we have a scheme where we have a president and 2 vice presidents, or first vice president, second vice president. Currently, I'm the president. I got into that role under a revolving scheme, let's say. So as of last October, I'm president for 3 years, and the first vice president is Junya Yamakawa from Japan. The second vice president is Joseph Govestis from Canada, from McGill University. And we've got general secretary, which is Massimo Martelli from Italy, based in Italy, and the former Imamoto Institute. And we've got deputy general secretaries for each of the regions. Next one. Right, okay, this is something from last year's conference that was held in Yokohama, Japan. So annual conferences, that's the big thing that we do. Next one. Right, and this year we already had quite some activity. So we're continuing the DES webinars, like the event today, and then we did something new, which was a symposium a week ago. And Mihari Tikeste from Iowa State University, he was the host and the indicator. It's about mechanic, agricultural equipment, and for agriculture. That's for the lot of local industry there.
Is it me or do we
Think
not
we-
hear Dr.? Okay, we lost him, didn't we? Okay.
Yes, I think we lost him.
Okay.
You can fill in for what he's talking about here, Varsha. It may help.
Okay. Okay, we'll have Dr. Lutz come on whenever he does, but I think what he wanted to say in this slide would be to talk about the events that are going on in 2025. I forgot to send out the link, but there was a symposium, the ISU ISTVS symposium. They had a lot of technical discussion, and they're getting together some notes. We did post a summary on it, so I'll put that in the chat once I get off the screen sharing mode. We do have our annual conference, the annual conference coming up in Lebanon, New Hampshire. You should have gotten a notification from this that I sent out yesterday. So you can start planning out your whole trip. We did get a lot of abstracts and full paper submissions already, so they're currently the technical reviews are on the way. Dr. Lutz, if you ever get onto this, please do chime in so that we can finish this presentation. But there's a lot of things coming our way, and this is a little bit of a brief of the conference that is happening in October. So you will be getting more notifications on that. The early bird registration right now is going on, so please do check that out. The hotels also are now blocked under the conference's name, so you will be getting the conference rates by August. So please do book them in advance if you don't want to have any issues later on with prices and so on. So there is the conference website for this, which I put in the chat, so you can see all the things that we're up to there. We will be giving you more notifications in the next few weeks or so. Yeah, we've also done a lot of work with Physicist. Physicist is very, from what I've seen, very active in Europe. We've had a lot of collaborations with them, and we also, there are some conferences that we do, I guess, with them. And this is new information that I know that Dr. Lutz was working on, is to get out the small research grants to people who are willing to do. It's more of like support money to already existing research, and it's again to improve standards and other sorts of things. And you'll be getting notifications on this, of course. I think the last time they did this, they came up with the update of standards. The paper that was one of their deliverables that they had. So they're looking for similar initiatives to be taken amongst our community, and we will be giving some sort of support money for the same. So please do look out for this call for, for these grants. We're getting it done. It'll be on the website in some time. And there is also a new ISTVS working group. I believe this was approved by the BOD last year. And they're looking at, improving terrain measurements and characterization in general. So this will be put into place this year. I do think that Professor Takeste and Dr. Thomas Way from USDA will be leading this effort with mentorship of Professor Wong involved somewhere. So this is something that we will be kicking off too this year. So again, more notifications will be coming up, and this is going to be more of a discussion and suggestions that everybody will get to participate, and we will understand how to better do this. So again, stay tuned for this. And of course, Journal of Thermomechanics, which is the I want to say the journal that everything kind of goes into. And please do consider submitting your papers here. We've had a lot of papers. You can see a lot of full length and review articles. My favorite are the review articles, actually, because they do give a lot of information. We've had good citations, a good score. So consider submitting your, I guess your publications here. And I did put that link in the chat. It's an Elsevier publishers, Elsevier. And of course, the DES events, the digital events series, where I get to coordinate with different hosts and different speakers all over. We've had only 2 this year, so we will be busy coming up later on. We have other presenters coming on. Stay tuned for announcements on that. I do know that Bohemir Jelinek from CAVS he confirmed to be presenting. We also have James Hambleton from UK also to be presenting. So that would be the next DES event. But yes, we do do a lot of seminars in between the seasons of the conference. And if you ever want to talk at the seminar, please let us know, and we'll be more than happy to give you the stage. We also have student chapters on behalf of ISTVS. The first one, well, I was a part of that, so we at Virginia Tech got the first student chapter up and running. We still do have a lot of activities. Recently, we went to a local high school to talk about STEM and other stuff. So the Mississippi State University also, Dr. George Mason really, I guess, drove that. They also got a student chapter recently. Dr. Mehari Takeste is telling us that they're in progress too for a student chapter. But these student chapters will be really handy because we are thinking about competing against each other. So you'll be hearing more about this at the conference. We are introducing student competitions specifically for tired, or track design. So you'll be hearing more about this later on, probably in a DES session too. But we're getting the student chapters to compete against each other. But
University of Pretoria.
yeah, they're also very yeah, the University of Pretoria is also very much involved with the student competition. So thank you, and I don't know if Dr. Lutz is here. Did I do a good job?
I'm here. Yeah, it kind of dropped out halfway, and no, you did an excellent job, Barsha, as usual. Thanks for that.
Okay.
Yeah, I didn't want to intervene. I didn't have to intervene.
If you could give us some final words.
I
And
don't know. We hope for continued participation in this, right? So the schedule is kind of irregular for the DES, but it's always properly announced like a week in advance, if not more. So we are really counting on proper, on continued interest in this series of terra mechanics talks. It used to be called, what was the original name that Alex came up with a year or two ago?
Resource Initiative, RI.
no, lunchtime
No,
lectures.
lunchtime lectures.
I
That's
thought
what
it
I
was.
was thinking of.
I thought it was
Lunchtime
awfully
lectures.
cute.
Mm-hmm. Well, it's not lunchtime in Europe anymore, and in the US, not yet. So, because that's another challenge with ISTVS, but I guess we're managing well, is because we operate globally. Sometimes if we have meetings, like board meetings, yeah, we need to coordinate the time zones and find the right time slot that works for everybody.
Okay.
All right. See you next time.
Okay.
To
So
do the
I'll be.
closing remarks, George or Varsha.
Yes. I guess we're closing out. Thank you very much for your time, and it's been an enjoyable speech. Hopefully we'll have it posted out on the website if anybody wants to look at it at a later time. Thank you very much.
Thank you, everybody, and thank you, Dr. Phillip Price, for giving us such a great presentation.